Шахматный мир давно и бесповоротно захвачен компьютерами. Профи используют облачные супертехнологии для анализа, любители шахмат смотрят партии этих самых профи с теми же, но облегченными движками. В какой-то момент стало казаться, что программы достигли пика своей силы. Однако в 2017 году шахматный мир шокировало появление программы AlphaZero, которая, зная вначале только правила шахмат, менее чем за сутки прошла путь до сильнейшего шахматного движка в истории. Партии, которые были опубликованы, произвели огромный эффект на шахматное сообщество, поразив ярким остро атакующим стилем, который был так несвойственен компьютерным программам. AlphaZero показала, что вечные разговоры о ничейной и любой другой смерти шахмат, как всегда, преждевременны. Как программа сумела научить саму себя играть в шахматы на таком уровне? Как работает уникальный механизм поиска хода? Чем AlphaZero отличается от Stockfish и других шахматных движков? И что на самом деле значат слова Монте-Карло, нам рассказал в эксклюзивном интервью один из разработчиков программы, сотрудник компании DeepMind Нинат Тамашев.
Yeah, I mean, that's in and of itself an excellent question, I would say. So, Game Changer, I share reviews. I mean, I had the privilege of being able to read through the book, through the early drafts before it was released, and I was super excited. I thought that some of that analysis was simply mind-blowing to my own, chess understanding and level at the time. And when it comes to AlphaZero, because DeepMind is a reasonably large research group. I'm not exactly right now, especially since we're not back at the office, so it's not easy to see. But we are something like 1,000 people just working on artificial intelligence research. And even when AlphaZero was devised, we were still doing all sorts of different projects. I'm not sure if you've seen recently, there was a lot of work around AlphaFold, which was looking into it has a similar name. It's not a similar approach. It's just the branding, I would say. But that has looked into protein folding, which is a long-standing big problem in science, and has sort of solved it to a considerable extent. And this matters because it can be used in drug design and prototyping. And they've released some of the early protein structures for the COVID-19 as well. Stuff. So DeepMind is doing lots of different things, and as a company, we have a long-term mission to, as people would kind of half-jokingly say, solve intelligence, which means all aspects of intelligence in some ways in which we as humans understand it, and then use it to solve big open problems. So we're not only focused on games or chess. That being said, we do still have some work around chess and around AlphaZero, but rather than working in order to improve AlphaZero as an engine to make it stronger, which could have been one direction simply because we're not a chess company, we decided to do something slightly different. And I think you've seen probably this work we've done with Vladimir, where we were using AlphaZero to prototype different new variants of chess in case people are feeling kind of adventurous and want to try something new. Obviously, there is nothing wrong with classical chess, but there can be many fun variants, and some were indeed very fun of the ones we've looked at. And we're doing some other work in the background on essentially understanding the system better, exactly why it works well and why it does what it does when it does, in order to help us build on top of that understanding and use those insights either to improve AlphaZero ultimately, or to improve some of the other systems that we have at the moment. But there is still some work, and hopefully some more work that we will be talking about soon. It's actually quite amazing in that it literally knows nothing at the very beginning. It doesn't even know that it's supposed to mate to win the game. Doesn't even technically know how all of the pieces. So it's literally empty of knowledge at the very beginning, and it has several components kind of tied together. But basically, there is a neural network, artificial neural network, that looks at the chessboard, just vision perception, computes some kinds of features, intermediate insights from that board, and then based on a representation of those, outputs a set of candidate moves to look into, and outputs an evaluation of the position based on that those insights. And then with those candidate moves and evaluations that you get from every board, there is this algorithm called Monte Carlo tree search that combines those to actually search through the tree of possibilities, where it looks at candidate moves in a certain order, and it obviously aggregates the value assessment that it gets from the bottom of the tree when it unrolls all the way down. And at the end of it, makes some kind of a recommendation on what move to play. So at the very beginning of training, AlphaZero knows nothing. And this is just a randomly initialized network that plays random moves. And occasionally, some games would be won randomly after a long period of time, moving lots of pieces around. And based on those outcomes, whether a game was won, lost, or drawn, AlphaZero would update its network to make it reflect this reality that's been observed. So very early on, obviously, one of the first things it's going to learn is that mate is a win, being mated is a loss, and obviously there are different conditions under which you can draw. This is probably the very first thing that gets learned. Then it would probably learn a little bit of some configurations of pieces that lead to those mates, and then slowly roll it forward all the way to openings and the understanding of positional patterns. So there's very many games against itself. It looks at none of the prior human data. I don't have the exact number of how many games. It varies a bit, but there are like some tens of millions in any case of games that end up being played, at least is my understanding. And at some point during training, it starts playing, slightly more sensible if you look at the games, how they unfold. Then it's probably at some expert level, then grandmaster level, and then beyond. Mm-hmm. And at the end of training, after 1 million training steps, as we say, it has fully converged to the system that's been evaluated, that has played Stockfish 8 back in the paper that was originally published, and which is not to say that we couldn't potentially train it for longer, or that it couldn't conceivably maybe even get somewhat stronger, but this is just the setup which we've been using since. Yes, to an extent. So what the evaluation of AlphaZero outputs, it outputs the expected score. So from that position, how likely AlphaZero thinks it's to win, lose, or draw at the end of the day, which kind of contains all of these other pieces of information that you're talking about. Because in Stockfish, for example, how it works, you compute very specific things, as you've said, like safety or space, and then there is a formula that combines those into a score. Whereas AlphaZero doesn't explicitly involve any formulas like that. It just gives one thing in the end, which is the win percentage, the expected score at the end of the day. From a position, a more interesting question, however, and something that we've been thinking about, is whether AlphaZero itself learns to decompose that in some meaningful way. So if it's implicitly computing some of those things you're mentioning, but explicitly it's not. So explicitly it's just trained to give this final score prediction in the end. And Monte Carlo tree search, when it unrolls all the way to the end, when it looks at the lines move by move, it looks at the value as predicted at the end of those lines, so the win probability at the end of the day. And then if branching from a certain node in a tree, there lead to different values, it goes into some kind of an aggregate expected score for each of the nodes, and that gets backed up through the tree all the way to the candidate moves that you're considering, and then you choose which move you're going to play at your current position. Ultimately many of the other search algorithms that are used in chess engines. That's a very interesting question. So when we train AlphaZero, when it plays against itself and learns how to play chess, we use a single time control for that training, and that is around 800, or it can be a different number, but 800 worked well, lines for each move that are considered. And it goes to some kind of a depth that is also controllable. And that's when it's kind of artificially stopped and you play the move that's best at the time. But this is just how, in terms of learning how to play chess. What this ends up being practically, and it depends on the hardware that's running this, is either something like 1 second or half a second per move in terms of the speed of play. So there is a reason, I guess, why this is done this way, because when you play, well, not really bullet chess, but something of the sort, so like very fast play, without deep calculation, then this puts some kind of a pressure on the system to learn how to get fast, because it doesn't have a lot of time to produce a really good move. So it's useful as a training signal. However, when AlphaZero is actually playing more competitive games, if you will, obviously doesn't have to only think for this amount of time, and it can adjust to any kind of a time control. So in games that would last for hours, these classical time controls, it can think for a couple of minutes, do something different. Now, the interesting point there is that the team, I mean, everyone who's developed AlphaZero, because they were focused on the reinforcement learning and the learning part of the algorithm, ultimately to show that it can reach that strength. There has never been an amount of thought that's been put into how much thinking time AlphaZero should take per move, because from a human perspective, and again, I also play chess, obviously not to an extremely high level, but there are some moves that you can play immediately. There are some moves where this is a complex position, this is a critical position, this is where I think, right? And if you're able to identify what are the positions where you need to think more, what are the positions where you need to think less, then you can allocate your time in some smart way to really spend the time that matters. And we've never tried that with AlphaZero, simply because, again, we've had other research focuses. So when it would play these long classical time controls, so games we've done that were played in that fashion, it would literally take the expected game duration and how many moves it's expected to play, and then it would spend, because it doesn't have an opening book, the most time in the openings and slowly reduce, move by move, less and less and less towards later stages of the game, which is somewhat unnecessary if you think about it, because you don't have to spend the most time you will spend on a move in a game to decide to play d4 or e4 or something like that. It is really not an optimal approach. This is just the one simple people have tried, and this is what, I mean, still work reasonably well based on how AlphaZero has played the games where it was, benchmark against that older version of Stockfish when it was. But I think a very interesting question, like when it comes to thinking time, is whether there can be another component in a system like AlphaZero that will identify, well, this is the move where I want to be thinking more. And then we are talking about this adaptive kind of a control, which you've mentioned, which would then decide when enough is enough, when no more thinking is needed, or when much more thinking is needed. So that's something we haven't actually explored, but I agree that it's fully possible to do. There is no reason why it couldn't get done. And one way in which it could conceivably be done is by looking at in some very intuitive sense, the variance and the stability of the assessments that you get the lines. How does it change? How often does it change? Maybe even some intuition for how likely you are to maybe be wrong, the complexity of it, the margin of the lines. So there are some signals there that can be used, but identifying the best way of either terminating early or extending the computation, it's very much an open research question that we ourselves haven't addressed. I'm not sure, actually, because I haven't been following as closely, whether the theme, right, because it's obviously the open source version, like an intended replica, right? Whether that team has looked into that, whether they have a good time allocation strategy, but we ourselves have not done work on that. I mean, certainly it has to calculate in some sense through more. I mean, I would say because AlphaZero has learned the game by already having played against itself so many times, there are very many, I would say, basically all of the main lines of all of the openings that it already knows even without thinking. It's encoded in the network. So if you look at the candidate moves, the order of the candidate moves, their probability at the very start of the game, even without doing any computation, they're pretty much going to be the main lines of all of the openings that we know. So just looking at what this policy network, as we call it, proposes as candidates moves, like in the rule of Pays, it's going to be the Berlin and these types of things. In again, in Gambits, some of the other things that AlphaZero likes. So it already knows this because it's already played it so many times. But on the other hand, when you do let it think for and actually calculate, it does change its mind a little bit on preferences between some of the moves. And one of the reasons also is that it only ever played fast play games against itself during training. So when given more time, then it maybe starts appreciating things in a slightly different way compared to what it would play under fast play. But yeah, I mean, like all of the candidate moves are already theoretical. So there are no big surprises there, I would say. Which is not to say that you couldn't combine a system with AlphaZero with an opening. I guess the team just wanted to be a bit more open-minded to AlphaZero, potentially discovering something new, having some kind of a different preference. But yeah, I mean, if you really wanted to spend compute, you could even let AlphaZero itself run through many of those opening trees with more thinking and save that as an opening book and then use it in subsequent games. Again, when you're really trying to build the best chess engine, you can do all of these things to improve a system. I guess, from our perspective, I wanted to demonstrate that a system that learns by itself entirely end to end as a very ultimately simple system can do all of these things and do them really well. And there can obviously be all sorts of improvements made to make the game easier for a system like AlphaZero. So saving time in the openings by having some kind of an opening book. Similarly, we've never really been using an endgame table base, right? You could argue that maybe that can be plugged in. I think we even looked at some point at having separate networks for separate game stages, etc. So there are many things you can potentially do, but we were just aiming for simplicity as a proof of concept, rather than making the most complex system that does everything in the best way possible. So as I said, there is an artificial neural network that looks at the chessboard that has all the pieces, and then it's on a technical level, it would be a deep residual convolutional neural network. It doesn't have to be that, probably it can be something else. And these types of networks are used in computer vision in general, even for looking at natural images, obviously slightly different dimensions and depths and stuff. And it does some kind of an analysis of what it sees. So I guess one would expect for it to extract certain patterns. First, in layers that are close in the processing to the board itself, it would find some patterns and configuration of pieces, how they're positioned around each other. Then it would become more and more global, and it would learn to extract the right features for making the candidate moves and for giving that value assessment. And the way it learns that is, again, by so it gives this output, let's say, which is the value assessment, and it gives the output, which are the candidate moves. And when it plays against itself in games, because it's an iterative continuous process, it takes this snapshot of the network, produces those things, but then looks at what has actually been played compared to what it thought it would be played. So the suggestion for candidate moves is given before any move-by-move tree-like calculation takes place. Then you look at the actual move being played after the calculations, and you put them side by side, or rather, the list of candidate moves versus again what has been computed side by side, and you want to move your suggestions towards what the actual outcome was. Similarly, for the value function, it looks at what the game outcome was versus what it thought the game outcome is going to be, and you want to move it closer to the truth. So you look at these deltas in the output of the network, and then because it's all kind of mathematical, right? We call it a network, but it's one big function that's decomposable. We compute the gradients towards the parameters of this network with respect to the deltas that have been observed, and this is propagated through the network and moves and readjusts all of the weights, which can be, like, if we're taking an analogy to human brains, strengths of synapses between neurons, right? And that would ideally mean that if you were to put the same position passes through the network again, the output should be closer to what you've actually observed in a game.
So it somehow updates the patterns all the time?
yeah, it updates its own understanding of the game all the time. And it slowly moves them towards something that's correct and strong. So obviously at the very beginning, it's just pure nonsense. But then this pure nonsense starts taking shape. So there are some patterns that start being understood, and the network learns to see all of the right geometrical patterns at some point, and then it learns how to utilize them well. Yeah, I mean, I guess just a tiny difference here is that even though there are big differences between our brain and something like AlphaZero, many of these deep neural networks have been modeled, well, inspired by the brain, to put it that way. So there are still some intuitive ways in which we can hope to describe, but this is not to imply that the similarity is actually that strong. Our biological brains are pretty unique in many other ways. I guess when AlphaZero happened, one of the most revolutionary things for us was this concept that you can, in a domain that, well, we understand, but still, in a domain that is easily programmable into a simulation, and the game is a kind of a simulation, that you can sometimes, at least we've shown that on chess, shogi, Go, and so on, start without any knowledge incorporated in the system and end up with solving the problem. I mean, to a large extent, which is not to say that you cannot get better systems at AlphaZero, but you can come to this expert human and superhuman level without knowing anything. So in a game of chess, without even encoding, that a mate should be a win, or that this is how the pieces, or you shouldn't be losing material, or anything like that, a system can go from zero to a superhuman expert and develop a very human sense of intuition, where it even lies. I mean, in terms of the number of lines it calculates much less than Stockfish and similar engines do. Obviously, it calculates more than a human, because we as humans can't calculate that easily. But it sits somewhere in between, where it's this hybrid that utilizes a human-like intuition while still being able to do more computation. But I think that notion that you can start from scratch, from zero, and still get something really good was revolutionary at the time. Because even with AlphaGo, which happened before, so the game of Go was the first, obviously very complex game that DeepMind sort of approach to develop a reinforcement learning system for. And it was a bit different to chess because their computer engines were comparatively bad at the time. It's a much more complex game in terms of the amount of search that is needed to put moves. But the AlphaGo versions that played Lisa Doll, that participated in those successes and big events, they were bootstrapped by looking at human games, right? And then the system would still play against itself and get better. But it started by learning the very basics of what it should do from human play. And then when it learns how to model human play, it would continue by playing against itself and improving and reaching some kind of a final system. And afterwards, there was work that was done to improve the system to be able to learn without this initial training on human data. And then even on Go, I mean, obviously AlphaZero does the same as AlphaGo used to. So essentially what we've shown there is that one doesn't need to have this prior human experience and can just learn everything from scratch. And I think this is pretty useful, if we're open-minded beyond chess and shogi and going beyond these games to some of the more difficult problems that we face in science, in technology, in understanding all sorts of big problems, where if you can encode something as a simulation meaningful way, and if you know roughly where to start in terms of your parameters of the network, that you can hope to make potentially big impact and big discoveries that way. Obviously, it's still not trivial, but I guess it implies that the opportunity to do that is there, and I think that is exciting going forward.
Yeah. Okay, thank you, Nenad. Thank you very much, and we hope to see the AlphaZero still alive, first of all, and the second, developing and showing some more of the actually very beautiful chess stuff that it has produced over the past few years. Thank you very much.
Thanks.
Thank you, Nenad. Thank you. Bye.
Thanks.